So now I want to switch focus to semi-stable curves. So that allows us to get sort of reasonably explicit examples. I'll first give you a definition. So first let's do it over an algebraically closed field. So if I have y over f, where f is an algebraically closed field, and y over f has to be proper reduced connected, and at worst ordinary double points. For people who like to think in pictures like me, that means that this is the worst type of singularity you can have. This is called a semi-stable curve. That's over. Now it's right closed field.
So a smooth surface is an example of that?
Oh, I didn't write curve.
Sorry, I mean.
Yeah. Has to be a curve, of course. So the answer to your question is no.
Okay.
It was an example of what I wrote before. And now if I take a y over t, where t is a general scheme, this is called the same, a semi-stable curve with an of t if y over t is proper and flat, and all the fibers over geometric points are semi-stable curves.
Yeah, that is also doubtful if this is a good definition.
Why?
Because it is not of finite presentation.
Oh, that's true. I have to add finite. Julia warned me for this, and I forgot.
Yeah.
I have to add that here, I guess.
Yeah.
Because for fiber-wise, you get that because of
your
one of the
definition above.
Yeah, because of one of the things that I already put. I don't know which. But here I have to add it.
I mean, proper over a field in a theory, so proper things are
Yeah.
Oh, yeah, sure. Yeah, okay. So I can leave that out if T is in the theory scheme.
Sure.
Yeah. So why do we want to look at semi-stable curves? There's this thing called the semi-stable reduction theorem, and that basically says that if you have a sufficiently nice curve over a DVR, maybe smooth or something, then after some smooth is way
So you mean not the generic
the
fiber?
generic fiber has to do with the smooth generic fiber. Then after some extension of the fraction field, the generic fraction field, so the generic fiber, then if you take the integral closure of R in that field, then you get a semi-stable curve over the spec of R. No, the spec of this new
The
R.
minimal model, right?
But the
You
minimal
know the
model
existence of
has a semi-stable model.
Yeah.
Like the
Right, so there is,
basic
so what I said, there exists some this extension, and I guess that's
Yeah, but
No,
we,
it's
all
really-
we also have to pass to a model, and so it's only
Yes.
the nicer models that have this property.
Like if you take a non-semi-stable model and you bake it, the special fiber doesn't change.
sure.
So it cannot become semi-stable.
Okay.
Right? So you have to say, well, there is now also a nice one. For example, the minimal regional model is
Yeah.
semi-stable.
But anyway, what I meant to say, the motivation is that if you extend your base field, you can often get a semi-stable curve. Okay, let's see. Oh yes, and remark that the confusion we had there is not a problem because all these things are one.
Yeah.
And so again, then the main theorems from Peter's lecture applies, and that means that we have seen what that the zero is just base zero. Okay. So now I want to talk about the dual graph. So let me define it. I can define this a bit more broadly than for just semi-stable curves. So let y over a field k, field f, a curve, and yi, it's a set of irreducible components. I guess again with a reduced structure. Oh yes. Then the dual graph is a graph with some vertices and some edges, and for every yi we get a vertex, say vi, and for every pair yi and yj, so they have to be different. So maybe I'll like different. We get an edge vij, and we don't get any more edges. And also we just get one edge if they intersect, and we don't care how often they intersect. We just get one.
For every, you mean for every intersection point, or
No, just for every.
you get a
just-
complete graph, no matter what? For-
Oh, yes, for every pair that meet.
Oh, okay.
Sorry.
So there's at most one edge between every two.
So there is at most one edge between every two. Yeah.
Ah,
Well, but Liu does this for some reason.
it's incredible.
Do you want more edges?
I want one edge for every intersection point.
But this is also a thing
Okay.
in the literature. Like it's not.
But I guess multi-edge is
Oh,
something
Okay.
It's
Plus
a
you
state,
can have.
right?
Plus you can have one.
Because
one-
you want you want maybe the first homology group of this graph to be something.
Be patient. We'll see what happens.
Well,
I mean,
Well,
this isn't how I would.
I find this
we,
horrible.
we will indeed want the first homology group of this graph to be something, but that's fine. I can still have cycles.
We'll
Yeah,
see.
but not enough.
Let's see what happens.
You need more.
Okay, so.
Well, it's not your fault. I don't blame you.
You voted on the side.
So the theorem says if y over f is semi-stable, and we let y I tilde y I the normalizations. What else do I need? Oh yes, of course I need the dual graph. Gamma is the dual graph of y over the algebraic closure. This is the setup, and the result is there is a canonical short exact sequence which goes like this. 1 t, I'll tell you what t is later. And here I get okay, where this map is induced by all these pi i's combined, and T is a torus of rank equal to, and here I need that. I want the homology of this graph to be something. So this means the rank of the cohomology group of that graph, and I didn't know what homology of the graph was before I prepared this talk, and I decided not to not to say it as well, because I don't think it's. I thought maybe it's not really necessary. I mean, of course, to understand the theorem completely, it's necessary to know what this means. But I thought that even if you don't know what the cohomology of a graph is, you can quite easily look it up. And then the point is, this rank can be just calculated, and then you know the rank.
You can also just see it as a topological space, right, in a naive way, like turn your edges into.
I guess you could. Is that the same?
Yeah.
Yes.
Oh, that's nice. I didn't know that.
But the theorem is still not true, though.
It's not true at all.
This
Why
is
not?
from Vasse's complaint of the dual graph is.
It's way too small.
Yeah. Like, if you take two P1s and glue 0 and infinity together, then your dual graph is just a single edge. And
Right.
so you're saying the toric rank is 0, but it's not.
So, does that mean that I have to also do this for I and j the same, maybe?
No, you have to do what I said. Each intersection point gives an edge.
Yeah. Okay. So every intersection point you have an edge, and the endpoints of the edge are the things that are intersecting.
But I do think you should also allow I equal j.
Yeah.
Yeah,
Even
there's
that.
a lot of-
yeah.
yeah,
And then
for
it's
that
not an
example.
intersection point, but it is each singular point. So that is easier to say.
Yeah.
The edges correspond to the singular points, and each singular point has two branches. That is from your picture, and that is the map that sends an edge to its two ends. Yeah.
Okay. Then I'm not quite
Yeah,
sure.
you still want to do the case where I is equal to j. So actually, you can erase a certain difference.
The intersection is not implicit.
And I also, but if I is equal to j, then I get just some number of loops.
But you might get
Yeah.
some crazy
Yeah.
number of nonsense. I mean,
Yeah, so it's actually the edges really correspond to the singular points. There is a bijection. Yeah.
So I have to add this many loops.
Yeah. Yeah.
but
No,
Why not?
no, it's not the intersection. It's really the number of singular points. Your number counts how much times it meets the other components or so.
No, but this is I and I.
No, that's not good.
This
That counts something completely different.
Okay.
It's also negative. It's minus the
That's true, and I actually know that. So you're saying for
The number of singular points, cardinality of sing of bi of f.
But perhaps
F bar. F bar. Yeah.
perhaps in VLR, whenever they had I not equal to j, they said something like you just take the multiplicity, or you just like you don't count multiplicity. Maybe that's what they meant before when you said you just have one for every point of intersection.
Sorry?
I'm not. So I don't know.
Oh, when we do
before you
these
said-
points, there are also f bar points. Huh?
Oh, F is algebraically closed, right?
No, f is
Oh.
not algebraically closed here.
Oh,
So
okay.
there you should take f bar points. Yeah.
Okay. Then I'm not certain if this is the definition that
Yeah, that's
Dr. Bomer and Bernal give. They should, because they.
There is no choice.
They should. Then
This is what they should have done.
but then I wonder where I got my definition.
But you maybe looked up some definition somewhere else.
Maybe.
The definition you gave is in Liu's book, and it's just.
Oh, okay.
Ah,
Liu gives two definitions. One, I think, one of them is this. What he gives basically now both the definitions that we've seen, and I don't really, maybe I misremember also, but I think he gives both, and I can't remember why. Also, should this whole right-hand board be over like a separately or algebraically closed field? Because otherwise the irreducible
The
components.
statement
It already is. I mean, its definition of semi-stable
No.
curve is
Statement
over.
of the theorem is, but
Is the statement of the theorem? Sorry, what is it? Is F an algebraic? So
Yeah,
F is always an algebraic closed field.
That's
No.
correct.
well, no, but here
There
is
you go.
geograph of f over the algebraic closure.
Oh, I see.
So it's, I think we only have to do it for
That's your definition.
So
No,
F,
you take T is strength F, and then you look at the geometric fibers, which is.
so T, F is always a field? Is that?
Yes, yes, yes.
Okay.
F is a field. That definitely.
F is a field and F bar is what I think it is. Awesome.
Yes.
We don't know what you
separable
want.
closure.
It's an algebraic closure. It might be a different one than the one you were thinking. Right. But so the point is that I told you that we've seen that the connected component of Neron model is this Picard scheme, and well, at least over field, then we know that it's some extension of a torus and the same thing over all this.
Oh.
It's irreducible components.
So that thing is a product of Jacobians, right?
This?
Quotient. Yeah. That's
Yes, this
nice
is a product
thing.
of Jacobians, yes,
Yeah.
because these are all normal.
Yeah.
Yes, that's fine. Yeah. So then we've got a fairly explicit description of the Neron or the connected component. Okay. And so I wanted to give you a proposition where we actually make use of the structure of this geograph. So as in the setup, and we assume that gamma, that's the geograph of, should I now take, I guess this is special. Closure. Oh yes, special fibers. Assume that this is a tree, so no cycles at all, and all EI equals 1. Then we will need, then just for convenience, we're going to need some, yes?
We only have a tree for. Oh no, sorry, I'm confused. So the graph is defined even when the curve is not semi-stable.
Yes, yes,
But
yes.
then what happens if three components go through one point? Then the edge has 3 endpoints?
No, we don't allow that.
Why not?
That was like worst.
Because we didn't say
Oh.
the curve
Yeah. Okay,
I mean,
so
should-
I need to put something here.
like semi-stable.
Well, no normal crossings or so. I mean, you can always blow up until.
But it's over a field.
It doesn't matter. No, but I mean, if you think of what you want to do with it, you want to have a regular surface, and you can blow up the special fiber in points as to get it a normal crossings divisor with multiplicities, and then you can do your stuff.
Sure.
So that's the situation you want here.
Okay.
But I'm not. I guess that for the talk, it's actually enough to just assume semi-stable. You can do more, but I guess for a talk, just think of semi-stable lengths.
Well, maybe that's why you had this more general definition of graph, because your definition of graph probably made sense without the semi-stability assumption. It just doesn't make the theorem true. So
I see.
but that's maybe why there's also this other definition around, because in the
Maybe.
semi-stable case you need that.
That doesn't sound unreasonable. Well, just keep correcting me as we go.
No, there is no excuse. This torus part is always described correctly by the right
But maybe
graph.
Sure, but maybe for some other applications you're not trying to describe the torus part, but you still.
Okay, so just have some notation for some numbers, these intersection numbers. D is the GCD of these di, and we take it out and we get the di prime. So there, go prime, this is prime. And then the order of the group equals some ugly expression and the degree of VI is of course the number of edges that are attached to I. And moreover, if all the I happen to be 1, then the group is cyclic. So that means then that this part goes away, and then we also know its order.
But I think that this proposition uses the first definition of graph, doesn't it? Because if the graph is a tree and all the di are 1, then it seems like you're actually in a semi-stable case, and so the graph is the order of component should be 1 if it's compact type. So I think this proposition maybe uses the other definition, the first definition of graph that you gave. Because this doesn't seem to be true with this definition of graph.
I'm not an expert, I just followed the reference and I didn't notice if any definitions didn't make any sense.
Why would it not make sense?
Because if you're in a semi-stable and the graph is a tree, then we know that the Jacobian.
No, you can have additive reduction stuff. I mean, this component group doesn't have to be trivial.
But if we're in the
Yeah, if all the di's are equal to 1, then I don't see why you would get anything at all. Indeed.
Right. But I think.
Well, maybe you could still have these EIs, right? That
But
could
we
be
said they're
every
all
stuff.
1. We're all EI are 1.
Oh, the EIs are 1 there. Ah.
But also,
Yes, all the I's are 1.
but also these AIJs don't make any sense, right?
Yeah.
Use this interpretation of the graph.
Yeah.
Because they would be 1.
So I wrote down the names
Yeah.
of the numbers of the propositions or theorems or
Well,
what they're called.
no, they would not be
DLR.
1 because there are residue fields. They have
yeah,
degrees.
yeah.
Huh? So actually, yeah.
I know, but you
But
do it over
but
the
then
closure, right?
Okay.
So, so I think
So
this is with the other definition.
can we have an
of-
example where we see this with a cyclic non-trivial group? What does it look like?
I can't do an example on the spot because I'm not an expert, and at this point I'm
Okay.
terribly confused and I don't know what the definition is. So definitely the answer to that question is no. I can give you an example where the graph is supposed to be a tree, at least according to BLR, and that is if JK has potential to reduction.
Yeah, because then the toric part must be 0.
Indeed, and that's the proof, because then the toric part is 0, and
Yeah, then your
So
H
this
rank
rank is 0. Yeah.
is 0.
Oh yeah,
and
so
there are
then
no-
this rank is 1,
Yeah.
and then it gets down. That is it, right?
Yeah, so indeed, I mean, I've just looked up the numbers, and they're just using different kinds of graph. Like there's two different graphs.
Really?
You've given two different definitions of graph. One of them is the proposition.
Okay. I apologize.
Bizarre.
Yeah.
Okay.
So the second one is on, the first definition you gave is on page 279, and the other one I still need to check. But it's just,
Okay.
There's two graphs.
There's two graphs. Okay. So exercise to the reader, find the definitions.
Well, connect the right graph to the right theorem. Or actually find which theorem.
Well, the theorems I pointed out the numbers. Actually,
Yeah.
the thing with the actually this they call an example.
To be fair, the definitions of the two graphs are both the paragraphs immediately preceding the statements.
Okay.
So they're not so hard to find. But yeah, you do have to notice that they're not the same. Which is, right. It would be nice if they remarked on that.
That would be nice
They
indeed.
gave them two different names.
Or yeah.
The dual graph and the dual prime graph. Or something. The dual silly graph and the dual real graph.
Okay, so I will.
If Reno is watching our video, we're in trouble.
No?
Here's a theorem that I thought was quite cool. If we take g to be bigger than 0, there exists a constant m of g such that for all r and x as in the setup, and maybe at some points you need strictly Enzelian. I'm not entirely sure what you think. Satisfying a few properties. Where a few is 4, K has to be algebraically closed. X over K has to be proper, smooth. So that's the generic fiber. Generic fiber has to be proper, smooth, geometrically connected. I guess that was already included. So it's geometrical integral and of genus G. Moreover, JK has potential reduction. So we're in the 3 case. And X is a minimal regular model over R. So that's why we take G to be strictly bigger than 0, because we've just seen in Ravenstorm that that's not going to happen if G is equal to 0. Then does it make sense? Doesn't it? There's that all. The order of this component group is bounded from above.